Okay, in the last few videos, we've discussed MaxEnt and discussed this idea that MaxEnt is the idea of maximizing entropy subject to certain constraints. And now we meet our very first constraint. And so we'll look at this constraint, and from this we will derive a full-fledged probability distribution. This constraint is the normalization constraint, or what I have come to call constraint 0, and the reason for that will be clear soon enough. And the normalization constraint normalizes our distribution, which simply means that it fulfills the requirement of probability distributions that the sum or integral of all possible values, the probability of all possible values is 1. Right? So we can take the probability of every possible value in that probability distribution and sum them or integrate. In the case of continuous distributions, that sum or integral should come out to 1. Okay? Now, you might, well, the slide gives it away, but you may be able to just reason yourself to the fact that when this is the only constraint, we come out with the uniform probability distribution. And this implies then that for any given range of data, the uniform distribution is the distribution with the most entropy, the most uncertainty. And any additional constraints we impose will decrease entropy from that point. One final note about the normalization constraint before we get into this is that of all of the constraints that are possible, only the normalization constraint is required, okay? And that is because it is fulfilling, again, this definitional requirement of probability distributions that they sum or integrate to 1. Okay? So no matter how complicated our distribution, this constraint is always a part of it. Okay, so before we look at constraint 0, I want to place this in a larger context of constraints, and specifically moments as constraints. And the reason is because the zeroth constraint can be thought of as a constraint on the zeroth moment, and that goes into the namesake that I've given it anyway. Okay, so so if you're not familiar with with moments, we'll go over that, and we'll see more of these as we push forward. But a moment denoted m, and then m sub k, where the k is some number, because we can have the first or the second or the third moment. Okay, the k represents which moment we're talking about, is simply the expected value of our variable y to the kth power. Okay, and so to get that right, we take y to the k for every probability of y and sum or integrate all of those, and that gives us the expected value of y to the k. And of course, for the continuous case, we have integrals instead. Okay, so notice how this fits perfectly into our earlier discussions about what these constraints look like. They are expected value of a function of y, and here that function of y is y to the k. When we are trying to estimate a moment, right? So what you see above there is theoretical moments, right? But the way that we get an estimate of the moment, the sample moment, is to take y raised to the kth power and then sum it over each instance of our data and divide by n, right? So it's the average of y to the k. Right? So that holds for continuous or discrete data, right? Because we only have discrete data points, even if it comes from a continuous distribution. Okay, so the zeroth constraint, again, the normalization constraint, is just fulfilling the requirement of probability distributions that they sum or integrate to 1. Because of that, it is the only constraint that is always required of our MaxEnt distributions. So there's different ways we can write the normalization constraint, right? One way is that we have the probability, the sum of all probabilities needs to sum to 1 or 100%, right? Which we've only mentioned about 7 times so far. Okay. We could write it this way, right? So we could just take the 1 over to the other side, and then that term becomes 0, of course. Okay. Or, as I alluded to previously, we can write it as the zeroth moment, right? Because y to the 0 is 1, the expected value of 1 is 1, and of course that is also the sum of the probability distribution. And as always, the logic holds for continuous distributions by replacing sums with integrals. Okay, so when we impose just the normalization constraint, again, hopefully as we move along here, it'll become clearer and clearer why this will give us a uniform probability distribution. In this case, it is just simply that the only thing that we are assuming is that our probability distribution sums to 1. And if that's the only constraint, then it leaves entropy or probability evenly spread among all possibilities. So we have our constraint, and now it enters into our Lagrangian, which we touched upon in the last video, like this. So we have our Lagrangian, we have an entropy term, and now we just subtract off the normalization constraint. Okay, so we have the normalization constraint in parentheses there, and it has its Lagrange multiplier, right? And again, the Lagrange multiplier is this little parameter that we solve for, but it tweaks everything to fulfill the Lagrangian, basically. So we'll see how we solve for it. It's a little bit hard to say exactly what it does and how we solve for it without just looking at it. But this is how the constraint enters into our Lagrangian, and from this we will solve for our probability distribution. And the way that we do that is to take partial derivatives of our Lagrangian. So we have our Lagrangian reproduced up there. And now we take a partial derivative of the Lagrangian with respect to each yi. Okay, so for each data point, we take the derivative of that Lagrangian with respect to that probability yi. If that seems a little bit weird, notice that in the Lagrangian, the py certainly contains the value that we observed, right? So in other words, that py is any generic value, but what we actually observed was y sub I, and certainly that is part of the random variable y. Okay. So we take the partial derivative of the Lagrangian, we set it to 0. And then we solve for the probability of y sub I. And in this case, what you see at the bottom of that boxed out section is an intermediate form of probability of yi. Now that intermediate form is important because we will here go on to solve this analytically from there, right? But later distributions are going to be too difficult to solve analytically, so we'll have to rely on numerical methods. And so we will need one of these intermediate forms for the numerical solution. Now, once again, notice that our probability of y, the expression e to the negative 1 minus lambda 0, does not depend on the value of y. Right? So in other words, it is the same for each yi, and this is again another hint that just having the normalization constraint is going to lead to a distribution in which all outcomes are equally likely. Again, the uniform distribution. Right? Well, I should have clicked that a little bit sooner, but that's okay. All right. So like I said, we're going to solve this analytically, and there might be one little question here. So right now we have n equations, right? So each of those partial derivatives is an equation, but we have n plus 1 unknowns, right? We have the unknown of each probability, y1 through yn, as well as our Lagrange multiplier, right? And so in order to solve this, right, we need as many equations as we have unknowns. So where is this additional equation hiding? Well, that additional equation is just the normalization constraint. Okay? And so you can work through the math there, where we take the normalization constraint, we convert it to our intermediate form of the probability distribution, and push through all of the math there. If the sum there doesn't make sense to you, check out the appendices in the book. They kind of go through these taking these sums. Sometimes that can be a little bit difficult. But what we come out with ultimately is we have the constant e to the negative 1 minus lambda naught taken outside of the summation, and then we sum 1 over all possible y. Now those possible y's are constrained between a and b, which are just arbitrary constraints. Okay, and so when you sum 1 that many times, you get 1 over b minus a plus 1, and that is the probability distribution for y, for all y's, again because they all have the same distribution, not dependent on y. Okay, and this is exactly the form of the discrete uniform probability distribution. Okay, so this is really interesting because we've gone from this Lagrangian that has all of these exponentials in it, etc., and we successfully derived a recognizable probability distribution, namely the discrete uniform probability distribution, and all distributions of the exponential family can be derived in this way. And we'll see a few more examples. This is the easiest of all possible examples, but we'll see some more later. Okay, so just because we were able to solve analytically in the earlier slide does not mean that we'll always be able to do that, that we'll be able to sit down with a pen and paper and come out with the solution. A lot of these problems will get too difficult to do, and in those cases we need to resort to numerical methods. Now we will always rely on numerical methods because they work whether or not an analytical solution can be found. So to kind of contrast these a little bit, when we solve analytically, there's more or less one workflow there, right? We started with the Lagrangian, we took the partial derivatives and solved for, set it to 0 and solve for the probability and so on and so forth. When we're solving these numerically, it's not, there's a few detours that we need to take. So it's not us just passing the problem to the computer and the computer solving it in most cases. What it is us working analytically for a little while until we come up with an intermediate solution like we have done so far, or did previously, and then asking the computer to solve a piece of that, and then taking those pieces and then doing other things with them. Okay. So numerical workflow is pieces of the overall workflow. So when we solve numerically, we start with one of our intermediate forms of the probability distribution. So hopefully that looks familiar to you. And then we identify our constraints, or now our constraints are written as residuals with MaxEnt typically. Okay, so we identify our constraints, and then we turn them into expressions of our loss function, or terms in our loss function here. Okay, so in that expression right there, the L refers now to loss function, not Lagrangian. I apologize if that is a little bit confusing. But we take our constraint, which is what we've done there in the brackets, and I'll point this out in a second. But we take the constraint and we square it, okay? And that is defining our loss. So let me unpack this just a little bit. So first of all, the b minus a plus 1 times e to the negative 1 to the negative lambda naught, that is just simply the sum of the probability distributions, right? So hopefully that makes sense. Hopefully you can follow that, right? So our probability distribution is e to the negative 1 minus lambda 0. And if we do that for every possible value, well, how many possible values are there? well, we previously found that it's b minus a plus 1, right? Because we have a discrete distribution that goes from a to b, and that's how many terms are in that, in that range. Okay. Now, so this defines a residual, our loss, so to speak, and we're squaring it. So there's a lot of different error terms we can use, and we will generally just use the squared error loss for ease of use, but there's other ones that are available, and one of the appendices in the online course discusses some of those, but this one works, adequately for everything that we need it to do. So what is this loss function doing? Okay, well, it itself is not doing anything, but what the computer does with it, that's our numerical, that's the numerical magic of our computer, okay? So this loss function, we will pass it to our computer and tell the computer to try to tweak the unknowns. Here it's just lambda 0, lambda naught, but we could have more and more complex distributions. And it will tweak all of the unknowns until the loss gets, to some minimum value. And here we hope that minimum value is pretty close to 0, minus some kind of rounding errors, very small rounding errors. But at that point, the constraint is satisfied, and then we use the computer. So sorry, I will be using R, and the function for this in R is called optim. So we use optim to estimate lambda naught by that process, that iterative process that we just kind of alluded to. And then we take the estimate for lambda naught and substitute it back into our probability distribution P of y. And that gives us then the probability distribution. And again, here, we will be when we substitute this back in, we'll arrive at the probability distribution. Here it's going to be a uniform distribution. Very, very basic example. Okay. So we had our intermediate form of the probability distribution, and so on the left-hand side here, we're going to write a loss function, and I'm using R. This is R language, but hopefully this is simple enough that you could adopt it to whatever your favorite language is. But we have our loss function. That's a function of lambda 0. We've defined this intermediate form of the probability of y, which remember is just e to the negative 1 minus lambda 0. And then we define the constraint there. Okay. And then remember our loss, we're just taking the constraint squared and then returning the loss. And now we pass that loss function to the workhorse of this process, optim, and under fn we pass loss function. Okay, and then optim will go through and give us a solution for any unknown in the loss function, here lambda naught. Okay, and so we can access that lambda naught with result. Well, we can access it. I don't want to be too specific to R in case you're not using R, but we can access the output of this process, and that output is the estimate for lambda naught, and then we simply substitute that back in for our estimate for the probability of y. Okay, so this is the final slide, and so I just want to make a few comments about why the uniform distribution is important. And I've alluded to some of these, but now we'll just kind of hit them home one more time. So when we only have the normalization constraint being imposed, it means that all outcomes are equally likely. And just by definition, we know that has to lead to the uniform probability distribution. Okay, so with minimal constraints, while still producing a valid probability distribution, we get the normal, or I'm sorry, not the normal. We get the uniform probability distribution, which implies that the uniform distribution for any range of data is the distribution with maximum entropy. All other constraints decrease our uncertainty from that point going forward. Right? So if we're going to constrain the mean, we inherently have less uncertainty. In fact, I think in the next video we will we will see this. We will constrain something besides, in addition to the normalization. Okay, so I believe that is it for this one, and we will see you in the next video.